Hi everyone. So we're going to continue our study of integrals of complex functions today. And the first question you might ask once an integral has been defined is there a fundamental theorem of calculus similar to the case of real functions? And the answer is yes, and that's what we're going to be talking about today. So before I state the fundamental theorem, we have to have a notion of antiderivatives, just like with real valued functions. And so here's the definition. If f is holomorphic, on a region G, so it's differentiable everywhere on this region, and if its derivative is equal to some function little f of z at every point in the region, so for all z in G, then we say that f is an antiderivative of little f on the region G. And this G is really important in the definition. It's gonna make a big difference in some of our computations. So you always, we're not just going to say, oh, we have an antiderivative. We're always going to say we have an antiderivative on some certain region. And we have to be careful what that region is. Remember, the definition of a region is just a connected open subset of C. So the thing to think of is an open disk, or maybe a union of open disks, which is still connected. Okay, so that's the definition. And maybe I'll do an example, kind of an important example of an antiderivative. So I claim that the logarithm function, which we defined earlier, is an antiderivative of the function 1 over z. In other words, the derivative of log z is equal to 1 over z on the region, which I'll write as c minus r less than or equal to 0. So remember, this is all, it's just the set of all z except for z with y equals 0 and x less than or equal to 0. So except for the negative real axis, we're looking at all points. And this is an open set, this is a region, and so this is the G in this case, on which we have an antiderivative. So the main thing I'm claiming here is that the derivative of log z is equal to 1 over z. And that's something that the book proved when they were talking about the principal logarithm. But let me just quickly explain the proof here. So recall, log z is an inverse function to the exponential function exp of z. And in general, if f inverse is the inverse function to f of z, then what that means is that f of f inverse, if I compose these two functions, I get back what I started with. And just to be a little bit careful here, remember exp of z technically doesn't have an inverse, so we have to restrict the domain of exp of z, and if we do that, we can define an inverse. And that's how we defined log, is we restricted the domain of exp of z and then on that restricted domain found in inverse. Okay, but if we have an inverse, then it satisfies this equation. That's kind of the definition of an inverse. And so we can take the derivative if both functions are differentiable, we can take the derivative of this equation, and the left side we can figure out using the chain rule. So the chain rule says that the derivative of a composition is I first take the derivative of the outside function, evaluated at the same place, and then I multiply by the derivative of the inner function, evaluated at z. And so that's the derivative of the left side. The derivative of the right-hand side we know is just 1. Okay, and the cool thing about this is it allows me to solve for the derivative of the inverse. So this implies that the derivative of f inverse is equal to 1 over the derivative of f evaluated at f inverse of z. Okay, and so in our case, f of z is equal to the exponential function. F inverse of z is our principal logarithm. And so this will allow us to calculate the derivative of log z. All we need to do is find the derivative of f, but we know that f prime of z, derivative of exponential is exponential, so it doesn't change. And so what this tells us is that if we take the derivative of f inverse, which is the derivative of log at some z, this is equal to 1 over f prime is just exp, evaluated at f inverse is log, and exp of log is just equal to z. So this is for z in the domain of, well, for z in this region that we're looking at, G. That's the largest, G is the largest open region in which this log function is continuous. Okay. Sorry, typo here. The z, exp of log of z is z, and so this is 1 over z. That's what I was trying to say. So the derivative of log z is 1 over z, just like in the real case. We just have to be careful of what region we're working on. And again, I chose this region G because this is the largest open set where log z is defined and continuous. All right. So that's an example of an antiderivative. Antiderivative of 1 over z in this region G is log z. Okay, and now let me state the fundamental theorem. So, well, before I mention that, just remember the fundamental theorem concerns integrals over some path gamma. Right? That's how we do complex integration. F is some function from the complex plane to the complex plane. We choose a path gamma with a direction, and we can integrate f over that path. Technically, gamma is defined as a function from the interval to the domain of f. And this blue line I've drawn here is just the image of this function, right? And so the starting point is gamma of A, the ending point is gamma of B. And these are the kinds of integrals we're talking about. Okay, and so then the theorem says suppose G is a region. And let's say capital F is an antiderivative of little f on the region G. And one other important thing is our path has to stay within this region. So let's say gamma is a smooth path contained in this region. So maybe f is defined on some domain G like this. I need my path to be within the region. And then if I have an antiderivative on that region as well, then the integral, the path integral over this path, is obtained just as the difference of the antiderivative function evaluated at the two endpoints of the path. Okay, so it has a similar feel to the first fundamental theorem of calculus. We can calculate this path integral by just looking at the values of the antiderivative at the endpoints of the path. Okay. Notice one interesting corollary that we get right away is so with the same hypotheses, same setup as in the theorem. So we've got a function f, an antiderivative capital F, etc. If gamma is a loop, in other words, if it's a closed path, closed just means that the starting point and the ending point of our path are the same, then the integral over gamma equals 0, right? Because in that case, f of gamma of b is the same as f of gamma of a, and so we get 0. And so what this is saying, in plain English, is if our path is a loop, and if f has an antiderivative on a region containing this path, then the path integral is going to be 0. Okay, so I want to do an example of 3 different integrals. So let's consider the path integral of 1 over z. That's going to be my little f over some path gamma. And let's do 3 examples to show kind of where this is useful and also where it's not useful. So well, maybe I need more space. So gamma 1 is going to be a path use colors. This path, which goes from 1 to I. Gamma 2 is a path, let's say we draw a circle, maybe a unit circle, maybe a different radius, I don't really care. So it's a circle centered at 1 plus I. It really isn't going to matter too much where the starting and ending point is. So this is a loop. And gamma 3 is, again, another loop. And it'll just be the unit circle, starting and ending at 1. Okay, so let's see if we can calculate these different integrals. So the integral of 1 over z over gamma 1 dz. So the fundamental theorem tells us, so we have an antiderivative of 1 over z in this region, and it's the principal logarithm, and so this is going to be equal to log of the ending point, I, minus log of the starting point, which is 1. And so we can evaluate this really easily. So log of I, this is, real part is ln of modulus of I, and then plus the imaginary part, so I times the argument of I. And for the principal logarithm, that's the one where the arguments, remember, we're avoiding the negative real axis, and the arguments go between pi and minus pi. Those are the angle measures that we're using. And so in this case, argument of I is going to be pi over 2. Okay, and then we're subtracting log of 1, which is just ln of modulus of 1 plus I times argument of 1. Okay, so what is this? So argument of 1 is 0. The modulus of I is 1. Modulus of 1 is also 1. And the ln of that is 0, because e to the 0 equals 1. So this whole thing is 0, this whole thing is 0. And we just get I times argument of I, so I times pi over 2. Okay, so it's much easier than calculating the path integral by hand, because we don't even need to parameterize the path once we have an antiderivative. So that was A. B. So we can just use the corollary, right? So this path is contained in the region G, where log of z is an antiderivative. And so since it's a loop, we know that, well, let me label this point, so I'll call this z naught. Integral of 1 over z over this path gamma 2 is just log of z naught minus log of z naught, 0. Okay, that was really easy. And then you might think part C is similar, or you may have realized already that it's not the same, because we know from class where we calculated by hand using the definition of a path integral that the integral of 1 over z over the unit circle path is equal to 2 pi I. So we did that calculation. If you don't remember it, try to do it by hand using the usual parameterization of the unit circle given by gamma of t equals e to the it. And it's not too hard to calculate this with that parameterization. But you get 2 pi I. And you might wonder, why are we not getting 0 as we did with the circle gamma 2? This is not 0. Because actually, we can't apply the fundamental theorem here. The fundamental theorem of calculus for complex functions. And the reason is this region G. So since log of z is an antiderivative of 1 over z, not everywhere, but only on this region G, which was equal to everything except the real axis for 0 and negative values. So everything except that part, right? That's where we have an antiderivative of 1 over z. But gamma 3 is not contained in that region. Okay, and since our path is not contained, because it has, it goes through -1, it's not contained in the region where we have an antiderivative, we're just not allowed to use the fundamental theorem. And you can see that if we tried to, we'd get 0 as the integral, which is the wrong answer, because we've calculated before that it should be 2 pi I. Okay, so you do have to be a little careful about where your antiderivatives are defined. And sometimes you can define an antiderivative exactly so that it is defined in the region where your path is, but in this case you'll never be able to do that. Okay, so that was all about the first fundamental theorem of calculus, and there's also a second fundamental theorem of calculus as well for complex functions. So here's the theorem. And remember, the second fundamental theorem tells you how to get an antiderivative. So how to define an antiderivative. So let's say, suppose we have a region, and we just choose some point inside that region, call it z0. And let's say we have a function which is continuous. And there's this technical condition, this extra condition that we're going to require for this theorem to hold, such that the integral of f is always equal to 0 on any path gamma whenever gamma is closed. In other words, whenever its starting and ending point are the same. So whenever gamma is a closed smooth path. Okay, so if this condition holds, that the path integral over any loop is 0, then I can use path integrals to define an antiderivative. So then the function, which I'll define in terms of path integrals, well, let me say it this way. Then I can define function f defined on the same region that little f is as follows. So I'm going to define f of z to be the path integral of little f, just write it like that, over a particular path gamma z, where gamma z is a path from z0 to z. Okay, and so the claim is that this gives me a well-defined function, capital F, and furthermore, this function, capital F, is an antiderivative of the function little f. So let me draw a picture to tell you what's, sort of illustrate what this looks like. So I've got my function little f, and it's defined and it's continuous in some region G. And there's some point z0 that I've chosen. And the way I define f of z is I draw some path from z0 to z, and I define f of z to be, again, the path integral over this path. Call this path gamma z of the function little f. Okay. So the thing you need to check, the thing that should worry you right away, is this function capital F even well defined? And the reason that it's going to work, the reason it is going to be well defined, is because of this condition that integrating over any loop is going to be 0. And if we have that condition, that's actually equivalent to saying that any two different paths from z0 to z are going to give me the same path integral. So maybe I'll call this one gamma z2, call this one gamma z1. So the question is f well defined? Is f of z well defined? In other words, does the value of f of z depend on the path gamma z that we choose? Because I didn't say anything about this except that it's a path from z0 to z. So there's many choices. And you should worry that it might depend on which choice we choose, in which case capital F of z is not really well defined. And so the answer is it's okay because of this hypothesis star that we had up here. So why is that? So let's look at these two paths that I have right here. So the claim is that the integral over gamma 1z of little f equals the integral over gamma 2z of f. And the reason is that I can, well, notice that this is equivalent to saying that the integral, okay, this is obvious, of gamma over gamma 1z of f minus the integral of f over gamma 2z is equal to 0, right? But if I'm integrating, I should put the directions on here. If I'm integrating along the path gamma 1z, and then I do the negative of the path gamma 2z, that's the same as integrating along gamma 2z but going in the opposite direction, then what I've essentially done is I've integrated over a loop that first goes along gamma 1, then goes back, the backwards direction along gamma 2. So I'll call this path, I don't know, gamma twiddle. And the point is, so integrating along blue and then the negative of the integral along red is equal to the integral along green. So this part here is equal to the integral of f along gamma twiddle. But this is 0 by our assumption because gamma twiddle is a loop. Okay, and so that's the reason we need that condition, is that if we didn't have this condition that integrals over loops were all 0, then this definition would not make sense because it would depend on the path we chose. But now it doesn't depend on the path, and so we get a well-defined function, and it turns out that it's an antiderivative. And the way to prove it's an antiderivative is very similar to the proof in Calc 1. Okay, I think that's going to be all for today.